Okay, thank you. So I'll sort of continue from where I left off last time. But I just want to clarify before I begin, I just want to clarify one small bit, one technical point. So because we keep using, I'll be using both of them. So to take two complexes x dot y dot C of A. So A is an abelian category, and this is complexes. A is abelian, and this is complexes. Then I assumed last time everybody is familiar with this, but just wanted to clarify that. So this, let's see. So we can think of this as, so I mean, this is actually, so 0 cycles. 0 cycles, which is degree 0 maps. Dot to y dot that go to 0. I mean, it's a cycle. Sorry, 0 cycle means degree 0 cycles in degree 0. Yeah, I'll call them 0 cycles. Go to 0 in the next degree. Modulo images. So these are boundaries. And that is images of degree -1 maps x dot to y dot. So okay, I'm not writing down the full definition of hom dot complex. So it's a double complex, and it's made out of a double complex coming from x dot and y dot. If one of them is a single module, then it is what you would usually do, hom that complex into that module, or that module into the complex. But if both of them are honest complexes, then it's a little more elaborate. And then this is, so one has to, I mean, there are some obvious maps, but there are also some signs here. And I just want to highlight that if you follow through the signs, so I'm not writing, as I said, I'm not going to write the signs here, or I'm not going to elaborate on the definition there. But if you follow through on the signs here, then what you will get is this side will be chain maps, x dot to y dot. And this side will be maps x to y, or homotopic to 0. So homotopic to 0 means there's a degree -1 map, and that degree -1 map composed with a certain way, that which is actually its image in the degree 0, and that is being killed here. So this is what it is. So therefore, this is nothing but, this is the homotopy equivalence classes of maps from x to y. That's the first point. And now if you take x dot and y dot, oops, this is a little high. If you take x dot and y dot in the derived category. So maybe I'm being inconsistent in the way I'm assuming things. If you are familiar with the derived category, probably you're familiar with this. But still, I wanted to highlight this part. So if x dot and y dot are in the derived category, then HIR hom dot x dot y dot. Well, oops. Yeah, that's right. So this is also the same, or we identify it with y dot shifted by I. And then this is by our previous thing. If you, I mean, okay, assume, so the objects of the derived category and the objects of the category of complexes are the same. So you can use this to then say that this is the same as, the only thing is, sorry, yeah, I have to be careful here. This is R hom dot. So here I have used hom dot, and the only thing to do, the difference would be to replace y dot by an injective resolution. If y dot is unbounded, then one uses so-called k injective resolutions. But for the time being, let me just say injective resolution. So then this is H0 of hom dot of x dot comma I dot I, where y dot to I dot is some injective resolution. And now one can say from there, this is homotopy equivalence classes of maps, but that by definition is also the same as hom in the derived category. This was all over A. Now, instead of hom dot from a complex, I've gone to a single abelian group, hom, and this is x dot comma I dot shifted by I, which is also the same as hom in the derived category x dot and y dot shifted by I. Okay, so that's the second point. And now putting them together, suppose I have two categories, A and B, and suppose I have, okay, so functors dA, dB, and this is a situation which we'll be looking at quite often. So f and g are functors both in this direction, and take x dot here and take y dot here. So consider the following two statements. First statement is I want to give a map like this, R hom dot fx dot y dot I. So these are the kind of statements I'll be looking at, and we'll come back to Worthier duality and Grothendieck duality in a short while. They'll all be statements like this. So this is one of them is, so this is in dB, I guess, and this is in dx, dA, and this is x dot g y dot. The other one, so there is some more information I'm suppressing here. So for example, these are triangulated functors, and there's a G and F will commute with translations. So all those statements, those are extra statements, but I'll suppress them in the background. And the other statement is the adjointness statement. They sometimes may not commute with translation. There may be a sign involved and things like that. So no, usually triangulated functors are not assumed to commute with, I mean, they are not assumed to commute with sign. What you have is, if you if you have a triangulated functor from here, what the part of the data is that if x dot is a complex, then f dot f, you only give an isomorphism like this. So when we say commute with translation, this is what we mean. That isomorphism has to be made explicit. And this via this isomorphism, triangles go to triangles. That's the definition of a triangulated functor. When I say it, actually they commute with translation. Sorry, I got carried away. I was thinking A and B are equal, and then maybe, never mind. So it commutes with translation in this sense. Yeah. Oh, sorry, R hom. I don't want to put the D here. So choose representatives and then just do the R hom. Thank you. And the other one is hom DB. So this is just a small technical point, but so I just want to say that, of course, statement 1 will imply statement 2 by whatever I have written here, because you can see that if you have because from this you can recover this. So statement 1 implies statement 2, and we quite often flip back and forth between them, but that is not to say that statement 2 implies statement 1. I'm not sure of that. But what it means is that in our context, quite often there's a natural way of going from, there's a natural way of inducing a map from one side to the other side here. If I have an explicit map from one of these objects to the other one, then statement 1 and 2 are equivalent. So statement 1 and 2 are equivalent if I have an explicit map in, let's say, the first one. This is a small technical point I want to say. And therefore, I'll be going back and forth between these two statements. Implicitly, it will mean that in my context, I will always find an explicit map from one object to the other. They'll always be there. Okay. So I'll go back to what I was doing last time, Grothendieck duality. And yeah, a priori statement 1 is much stronger. Yes, yes. But if I have a map in one direction, already away, if there is a way to construct a map in one direction from this to this or this to this, then they are equivalent. Because to say that they are isomorphic is the same as saying their homologies are equal. So therefore, in practice, one usually finds there is always a map like this. It's induced by some particular process. Okay, so Grothendieck duality, let me just remind you, was for a map fx to y of locally compact, continuous map of locally compact spaces. Of dimension, of finite dimension, finite cohomological dimension. And under this hypothesis, we had the following statement that essentially RF lower shriek as a right adjoint. So hom of dot E dot is isomorphic. So this is in the derived category of y. And this will be isomorphic to hom the derived category of x. dot so I promised last time I'll give a sketch proof in a very special case. So special case is when y is a point. I forgot, sorry. I think I'm, so it was not exactly y here. I was not looking at all abelian sheaves, had something more. D of, I'm not sure what notation I used last time, but let's say D of k tilde x modules. And this side is, sorry, k, y. And this side is B of k tilde x modules. And in fact, the duality is actually only for f dot. So maybe I should say somewhere here. What we have is f dot and g dot are in d plus. So d plus of, so f dot is in d plus of x. A x modules, and g dot is in d plus of. I will use the special case where when y is a point and A, I'll assume is a field. So let me remind you, I use the word finite cohomological dimension, and finite cohomological dimension means that so it means that the cohomology with compact support. So finite cohomological dimension means HIC x is 0 for I greater than some number. And then that number, the smallest such number is is the cohomological dimension. And if you recall, this is computed by using a soft resolution, or if you want, you can also use an injective or flask resolution, but in particular, you can use a soft resolution of F. And then just apply the sections with compact support functor and then compute its ith homology. So that was a definition of dimension. So let's give a sketch proof of this. Y is a point, K is a field, and so we may assume, we'll also assume that G dot is K. This assumption is not serious because if it's a field, if you're talking about a field here, then everything is a direct sum of translations of the field. So might as well just understand what is happening when G dot is just one copy of K. Okay, so in this case, F lower shriek is simply the sections with compact support functor. And so therefore, yeah. So the statement is that, so you can reduce the statement to saying that R hom, so this is just the dual part, hom, R gamma C x of F dot dual is isomorphic to, and this side is in the derived category of x, kx modules, and this side will be F dot, and then some mysterious complex F shriek of K. So let's first begin with that. So pick the proof of. So pick K to S dot a soft resolution K tilde, a soft resolution of K tilde X. So for example, if you are on a manifold, smooth manifold, you can use the dynamic resolution. Otherwise, we anyway said any injective resolution or flask resolution anyway do. So you just pick your favorite soft resolution. Then, and this, because it's, okay, so let's assume dimension of n is, dimension of X is n. And so this you can assume of length greater than or equal to n. In fact, length n is enough, but just pick any soft resolution. Sorry. No, I think I want length n. Okay, let's take length n. So there will always exist a resolution of length at most n because, so I need to say that. So right now, maybe, okay, so this might be a bit confusing. So let's say finite length. Let's play it safe. But in fact, one can show that the length is bounded by the dimension. That's because looking at HIX f dot or HIU f dot, vanishing of HIU f dot for every open set U will in fact imply that f is soft. So f is soft if and only if these functors vanish for every U. That's because you can then show that you can, on the complement of U, if there is anything, you can lift it. So by, when you have a long exact sequence relating sections on Z, supported in Z, sections on X, and sections over U. So you can use that. But anyway, right now we know by definition there will exist a soft resolution of finite length. Okay. So then I will use this to, so then we will use this to give the definition of f apostrophe k. To define for any sheaf Fs on X, we define a new sheaf or rather I should say free sheaf, which I'll call S hat, given by U goes to sections with support and then dual. So instead of dualizing all the sections, I just dualize those with compact support. And this is a sheaf. This can be seen to be a sheaf. Oh, I should mention some reference here. If S is soft. In general, it's not a sheaf. So by the way, I mean, almost everything on Verdier duality that I'm presenting can be found in this nice book by Iverson. Maybe I should write here because I'm not going to. Homology of sheaves. So, yeah, you can find all this there, for example. Okay. Yeah, so I'll leave this part. Essentially, again, you use the fact that because it's soft. So what you have to do is you have to, given two open sets, for example, you want to say that, you want to say it's a sheaf. Yeah. So given two open sets, which if I give you one section from each one of them, which agrees on the overlap, you want to say you get a section on the whole thing. but this is dualized. So write down the dual sequence, and then you can view it as some exactness, right exact. I mean, you can view it as a statement on some right exactness. And that will happen when S is soft because H1 vanishes. So roughly that is the idea. And so one can show that this is a sheaf. And once we have that, then all I'm going to do is dualize this and call that as f of k. So we'll use f of k equal to the dual of this. So it's a sort of an abstract proof. Immediately it doesn't reveal anything. It will just give the proof. Does not tell us how to compute it. But then later on, I will say a few things about how to compute it in the case of, in our familiar case of manifolds, and why it gives Poincaré duality. All right. So let's check that this works. Okay. So what is it that I have to prove? So again, I will prove this more at the level of complexes rather than just at the level of derived categories. So let's write down hom dot. So R hom dot. But Y is a point, and so this is just is a point, and K is a field. So dualizing in the derived category is just ordinary dualizing. So we will cut down on notation, and so we'll just say, so the first thing on the left hand side is x f dot dual. That is what this term is, because G dot is just K, and then this is just, didn't I say somewhere? Yeah, F lower shriek is cohomology with compact support, and then this is, that's what it is. And the right hand side, you will see is, what is it? So this is F upper shriek K, which is what we have there, S dual and F dot. Okay. So R hom dot. Sorry, F dot. And I want to say these two are isomorphic. So I'll make three claims. First, that this is the same as gamma C X F dot tensored with S dot dual, where S dot is whatever we have picked here, resolution. And the second claim is that this is isomorphic to hom dot F dot S dot. Again, here there is a dual. And then this is isomorphic to this. So this is how we'll finish it. So this is part 1, this is part 2, and this is part 3. Yeah. This one here? Yeah, I'm interested in F upper shriek of G dot. Didn't I say I will be? Oh, sorry. Yeah, I mean G is K. Yeah. Kx still I should call it. Yeah, G dot is just K. That's just a field. Sorry, this is just a field. Yeah, go ahead. Yeah, because G dot is a complex on the point Y with coefficients in K, so it's a bunch of vector spaces. And so might as well just know what is happening when it is a field K. So if you know, if you prove it for that, then you prove it for others by just taking direct sums. So okay, so proof of 1. So of course, this is a quasi-isomorphism because K is a field, so everything is flat and exact. So this is certainly a quasi-isomorphism, but that's not enough. The next statement I'm going to make is that F tensored S over K is soft if S is soft. And that will help us prove one, because then, if you have soft resolutions, you can remove the derived part, replace R by. So this basically is proved as follows. You take what is called as a, so you take a flat resolution of F in the following way. So some PM. Where M is greater than the dimension of N. And PIs are direct sums of, so some flat sheaves. And these flat sheaves are obtained by extending via 0 is a direct sum of, also direct sum of sheaves of type J lower Schwick. What does that mean? Basically, I will have sections over various open sets, and given a section over some open set, I just map a copy of J lower Schwick K tilde U to that section, because this has sections only over U and it is 0 outside U. So given a section on U, I can simply give a map from this to F, which sends the generator on 1 on U to that element, to that section. And so given such sections over various open sets, I can take various direct sums like this. So it's equal to direct sum of sheaves of this time. And so I can always map a surjective, I can always find a surjective map like this from, this is a flat sheaf from P0 to F. Nothing to say flat here because K is a field, sorry. From a sheaf like this to F, and then look at the kernel and repeat this process. So to check that this is soft, I will tensor this with F, with S. And so you have F0 and then I have PM tensored S with K. K tensored S and then 0. I have an exact sequence like this because I am tensoring over the field. Sorry, here, I mean, these are sheaves, but you tensor them over K. So, sorry? F tensored S. Sorry. If you want, you can put Kx tilde here. You're tensoring them over Kx tilde. So you have an exact sequence like this, but these are all already soft. And that's because if I take a sheaf like this and tensor with S, then it amounts to restricting S to the open set and putting a J lower Schwick to that. So use this fact, which is easy to prove. Basically restrict to the open set and then push it forward by extension by 0. And this is soft. So this is soft. So this is actually the main thing, and then everything else will now follow from this kind of argument. So I have a bunch of soft sheaves here, but we know that the cohomology vanishes after a certain number. And we have taken a resolution of length more than m. So one can now argue that this implies F tensor S is soft. Because m is greater than or equal to n. And now everything else will be a sort of a similar argument. Number 2 and number 3 will be a formal consequence of number 2 actually. So or something which looks like 2. So let me just finish this part here. Okay, proof of 2. Yeah, I think what I'll do is I'll just indicate that. So what is 2? Yeah, I have it here. So one can show that there is a natural map . First at the sheaf level. So here's a sketch proof. One has to first show that there's a natural map like this. And it requires a little bit of work, but once you are able to set up this natural map, then what you can do is you can again just check that this natural map is an isomorphism when F is a sheaf of this kind. Because then this is just what this gives me is gamma U of S. And this side will be Hom. This side will be S hat of U. I mean gamma. That's the same thing. Or let me just say Hom. Let me write it out what it is supposed to say. Hom. Which is just sections of S hat over U, but that's exactly this one. So this is an isomorphism. And so once you set up this natural map, then you can check that this is an isomorphism for F of a special kind. And then you use some kind of phi lemma, because again, you can write down a two-step presentation of F by such sheaves. And for such sheaves, one can check that this is an isomorphism. So you can prove it for F. So not phi lemma, but whatever, some similar lemma. So and then just apply this. So I will skip the part of actually carefully checking that there's a natural map like this. But if you insist, I can say what that map is. And the third part is actually a formal consequence of this statement here. Because if you think about it, I need to say something. A third part follows from the fact that, in fact, S hat is an injective module. And that will be enough, because then we are just dropping the R. And so we just have to show that S hat is injective. Just stare at this, and you will see that you are looking. I mean, if you put any exact complex f dot here, you are so you want to check this is exact, but that's amounts to checking this is exact. You can put sorry, but tensoring with S is exact because it's over K, and we saw that this is soft, and therefore gamma C x f dot tensored S will be an exact complex, and then you dualize it, that will be exact. So this is a formal consequence of the isomorphism in 2. That actually finishes the proof. Yeah. Yeah, there is a, you have to set up the natural map. Then when f is equal to j lower Shri ku, you can check that it's an isomorphism because you can identify the left-hand side and right-hand side like this. And therefore, it's also true when you use a direct sum of such sheaves. And therefore, it's also true when you have a presentation by such. Somewhat formal proof. I can also indicate what happens when K is not a field. If K is a Noetherian ring, a similar proof goes through. But what you have to do is two things. One is you have to find, so this soft resolution should actually be a soft and flat resolution. Somewhere, where is it? Yeah. So if K is not a field but a Noetherian ring, then you replace S dot by a soft and flat resolution. How do you find that? Well, you use the Godma resolution, so the canonical Flask resolution. So start with your field. This, of course, has sections all flat over K, and then use the Godma resolution that I said last time, assigned to every open set direct product of the stocks. Then that will automatically be flat again, and then iterate this process. So if you just apply the Godma resolution, you'll get a flat resolution, which is also Flask and hence soft. So use that. And when you, on the other hand, when you dualize here, you will have to dualize it with respect to some injective K module, because of course, when K is not a field, you cannot simply assume G dot is K. You'll have to assume G dot is a complex of injectives. And so you will have to dualize it with respect to a fixed injective module and check this. And therefore, you'll have to make the same state. But once you assume that you are dualizing with respect to a fixed injective module, everything else again holds. All these claims hold. You can show that if S is flat and soft, then this is soft. And what else? You can give this isomorphism, and then you can deduce this kind of thing. And so you put everything together, you modify the proof accordingly. So if K is a Noetherian ring, you can still almost similarly give an almost similar proof. So maybe I'll just write one sentence. If K is Noetherian, K flat and Flask resolution, which implies soft. Using Godma. That's one thing, and the other thing is this dualizing process. We dualize with respect to K. That's because we were, in some sense, here this was going to be K, but now you cannot assume it's K anymore. So it will be some other complex, but that complex can be replaced by an injective complex. So you dualize with respect to injective. Also, for any injective, A injective, G over K, you'll have to dualize it for every possible injective module. Use S dual will be U goes to Hom gamma U S into G, gamma C U S. You have to use that instead of just the vector space dual of gamma C U S. And then just go through again the whole proof and just check that you can still fix it. And finally, if Y is not a point, then also actually the same outline works, but again, you have to do more modification. So I'll skip that part because anyway, I promised a sketch proof in a special case. So I refer to the book by Emerson for more details. Before I describe why this gives us Poincaré duality, I will end with the intriguing question posed by a student. Can you use, and I don't know the answer, so. So this is the proof that I have sketched here is a very sort of 20th century proof, but the last 2 or 3 decades, we have had other kind of arguments coming into these kind of theorems. And is there a proof using Brown representability? I don't know the answer. There is a theorem. Okay, I don't want to write the state, but it basically says that if you have a homological functor, meaning if you have a functor from a derived category, so let me pick one derived category. Where is the derived category? Yeah. Okay, so if you have a functor from one derived category to, let's say, an abelian category, which sends triangles to long exact sequences of it's a homological functor. So it sends triangles to long exact sequences of abelian, whatever the object in the abelian category. Then if it commutes with coproducts. Okay, so now it depends, the assumptions vary. So this is the basic requirement, that it should commute with coproducts. Because you can show that if a functor has a right adjoint, then it has to commute with coproducts. That's an easy formal consequence of the existence of right adjoint. So that's a prerequisite. So if it commutes with coproducts and one more hypothesis holds, then you want to say it's a representable functor. And using that, you can set up the adjointness. But that one more condition will vary from context to context. Initially, for example, you can say there is a compact generator for the category, but people have sort of found other replacements for these assumptions. And there are theorems which might apply in this situation, but I've not gone through the whole thing. So it is, yeah. So it's representable. It's saying it's saying when it is representable. And sorry, I mixed up two things. But yeah, it's saying when is a functor representable, and using that you can then show that if a similar using that you can then show when a certain functor is has a right adjoint. So there are two things. there's a representability theorem for a cohomological functor. And using that result, you can show that you can apply it to a certain situation and you can prove whether the functor has a right-edge joint, whether the triangulated functor has a right-edge joint. So using those ideas, can one prove it in this case without having to go through a proof like this? I don't know the answer offhand, but there might be a proof. Okay, what I promised was to show that this implies, how much time do I have? Yeah. I mean, I don't know whether it's called soft proof, but yes. I mean, yeah, that I have no answer to that. I mean, all I can say is that verification is probably this kind of argument is what is making it happen, but it doesn't really reveal anything. I mean, it doesn't say anything about it. I mean, this kind of argument, as in taking a resolution of this length and checking it over these kind of sheets. That is somehow what is being used throughout. But I mean, that is, I don't know anything more to say about it. Okay, so back to locally compact space. Sorry, no, not back to locally compact spaces. Yeah. So here are some to check that this gives us Poincaré duality. One needs to do some explicit calculations, and those explicit calculations can be found in Everson, but those are nothing surprise because there's no surprise in them because it's similar to what you would prove in any basic course in topology. So one proves. I'll write down some facts because I can then use them to say something about how Poincaré duality is coming out of this. So these are very explicit calculations. So for example, take this space. The only thing which you may not, yeah, I mean, here I'm allowing any ring, for example. So this is for I equal to 0, I greater than 0. So this is proved by some sort of induction on n, proved for n equal to 1 using the exponential sequence, and then somehow write it as a fact, write it as a fibered space over smaller dimension O1. And the fibers are also of the type O1, and you use that. I'm not writing subscript to the k tilde here, but it's understood k tilde on this particular space. So this is again as expected. This is k here if I is equal to 0 or n and 0 otherwise. So these are the standard things that you would expect any cohomology, any this kind of compactly supported cohomology satisfy. Say is k if I is n and 0 otherwise. So this is the open disk. And again, same thing. But not just that, I would say that this is an isomorphism to HICRN k tilde under the inclusion map. So, so in all this, I should say there is a Meyer-Vietoris kind of sequence available for cohomology, and one just applies that also. The first one is requires a little bit of work, and after that it's all mere weighted kind of argument. The thing which may require some more work again here is one fact. Homological dimension of Rn is exactly n. That it's greater than or equal to n is already written somewhere here, because we can see that at least there is one situation where the nth cohomology doesn't vanish. The claim is that that's in fact the bound. I mean, this is again expected. Yeah, this sort of kind of an induction kind of argument. Again, I won't write it, but you break it down into, you take, suppose there is some high cohomology which doesn't vanish. Suppose there's an n+1 cohomology with compact support on some sheaf which doesn't vanish. Then you restrict yourself to closed subsets of this kind where it doesn't vanish. And somehow by Zorn's lemma and a limiting process, you can find a minimal such closed subset where it doesn't vanish. And then you can argue that that minimal closed subset has to be a point, because if it were not a point, you can break it up into two. You can break it up into two closed sets and use Mayer-Vittorius kind of argument to argue that at least one of those two smaller closed subsets, the section again doesn't vanish. And once you have shown that Z can be reduced to a point, you have come down to a smaller dimension, and then you argue by induction. So it requires a little bit of argument, some kind of induction, and using Zorn's lemma to find a minimal set over which the particular cohomology class doesn't vanish. And then to argue that that minimal set has to be point. And once we have this, then homological dimension of an n manifold is also n. And this is proved by arguing that softness can be checked locally. Softness of a sheaf can be checked locally. On a cover. That's a general fact, and if you apply this general fact, then since cohomological dimension of Rn is n, one can show that cohomological dimension of any manifold is n. And so what this means is that Verdier duality applies to a manifold. Okay, so now I can write down the promised statement, which is Poincaré duality. So as I said, I'm skipping over all the calculations and small details. You can look up yourself. So let's assume X is a manifold of dimension n and K is a field. Then F upper sheet K So there is nothing. So y is a point. So, so y is equal to point. So then there's nothing to write for k tilde y. It's just k, and this is isomorphic to just one object sitting in degree n, the orientation sheaf, where OR of n, or OR, sorry, is the orientation sheaf. In this context, defined via the obvious defined by sending U to HN compact support U k tilde. And one can show that it, okay, so this will also prove this, satisfying orientation, the stocks are isomorphic to K for all x in X. And therefore, in this context, the statement of Grothendieck duality gives us a more familiar version. Thus, HT x k tilde x is isomorphic. Maybe there's a dual. Yeah, is isomorphic to Hn minus p orientation. So this side is maybe something doesn't look right here. Orientation is the f upper shriek k shifted by n. Okay, it's on that side. Okay, good. Yeah. So there's a compact support here. And that's dualized, correct. So the one which is dualized is on the compact. So this is the usual. You can see that this is, if you put y is equal to point and x is your topological space, the statement is exactly that, this one. Once we prove this. But this is easy to prove because we have done, I mean, I have written down the explicit calculations. So from this, it follows. And from the fact that, so this is the key point, that since f shriek, or this is one interesting feature of this, since f shriek can be computed locally, which means if I have an open immersion, open subset U to X, gives implies F composed with J shriek K is isomorphic to J shriek F shriek K. That's just formal. And then this is isomorphic to F shriek K restricted to, because J shriek is restriction. So I didn't prove this, but you can easily, so this is easy to see that J shriek is, I mean, it's a right-hand joint. So if you find one functor which satisfies the job, you'll be done. And what you can check is that restriction satisfies the job. So restriction is a right-hand joint for J lower shriek. So that's a basic fact. once you assume that fact, then F shriek can be computed locally. And so if you can, since you can compute it locally, you can replace X by an open subset homeomorphic to Rn. And in that case, the statement is obvious. We reduce to checking when U is Rn. When U is homeomorphic to Rn. So now we conclude by explicit calculation. We have done the explicit calculations because when U is homeomorphic to Rn, then didn't we do it? We did. Oh, maybe I should. Maybe I am doing a bit. It should follow from these calculations. So if U is Rn. I just put F dot is equal to K, and then G dot is K, F dot is K tilde X. Then I'll get all the sections of K tilde X, which is all the things here. And we have already calculated the cohomology with compact support, and we have shown that it is 0. Okay, so maybe it needs to be written. Maybe I'm being a bit fast here, but probably one should use this duality there. So basically what we want to say is that what is the more explicit form in which I can say it? It's here. So when it is Rn, I can see that, when it is Rn, so I can see that R gamma Cx use F dot is equal to K tilde. So R gamma then put this dual, and then this is isomorphic to R home dot of K tilde X into the orientation shift. Dot dual, which is actually orientation shift. So this side is actually computing for you the global sections. So in fact, you can also put any open set U here. Let me use a different U. So let me call it V here. So we just do it for any open set V here. So this side is computing the various sections of F upper shriek K. And this side is telling you that every time you have a open set which is diffeomorphic to Rn, there is no cohomology except in the nth degree. There is no cohomology except in the nth degree here. So using this, what we see is that all the cohomology only lives in 1 degree of this complex, and that's measured by just applying this. And in that degree, it is just given by HNC. The sheaf which sends V goes to HNCV K tilde V. And that's exactly the orientation sheaf. V goes to HNCV K tilde. So if you just apply, this is Worthier duality statement. If you just apply this statement, This side is giving you, you are computing the cohomology of f of k, because this is just sections over over k. I mean, this is just picking out the sections of this. If you want, you can, this is over the field, over the space V. Not B, I should say, yeah, over. And this side is just giving you cohomology with compact support of k tilde V. But we have already calculated when V is isomorphic to Rn, we have already seen that only the nth one exists. So this implies that. So that proves this part. And okay, I'm not going to get any time to talk about Grothendieck duality, which is what I wanted to start with today. Okay, so let me just wrap up by a few comments here. I'll just keep this for ready reference. Yes. I mean, at least in this situation, yes. Yes. Yeah, if you can take this example. Mix manifolds of different dimensions. Then f of k will have to live in 2 degrees. Yeah, I mean, when you restrict to this plane, it will have to live in degree 2. When you restrict to this line, it will have to live in degree 1. And now it will have to live in degree in both the degrees in this particular example. Yeah. In which, yeah, I mean, in the case of a manifold, we have shown that it's just this one. Yes, yes. So this is in the derived category. This is a derived category isomorphic. But it's isomorphic to a single sheaf when it's a manifold. In this case, it is not isomorphic to a single sheaf. It will have at least 2 homologies. It will have 2 homologies, exactly. One corresponding to the plane, one corresponding to the line. What is the? At the intersection point, I don't know. I can, in the algebraic geometry setup, I can calculate it. In this setup, I have not, I mean, I imagine it's similar. I don't know, offhand, I don't know the answer. I mean, you are maybe interested in knowing whether it's a direct sum or not, or curious. No, it's a complex in the derived category. So he's asking, what does a complex look like at the point? What is a stock? That's still a complex in the derived category over the. Okay, in the algebraic geometry, I would say local ring, but now it will just be vector space at the point. So you're interested in the stock. So you just go to the yeah, the stock. So I shouldn't say vector spaces, but what should I say? Yeah, I mean, okay, whatever. It will be, yeah, it will be a complex of, sorry? It's a complex in the, it's an object in the derived category. Yeah, so it will be a complex. And he wants to know what the complex looks like. Homology, yeah. Right. So I don't know the answer to that question. I'm not that conversant with that side of the story. Okay, I think time is almost up, so I'll just say a few remarks. Yeah, this one I've already said. What you can also see from here is that if it has dimension n, if you have a not manifold, if you have a locally compact space of dimension n, this may not have just a single homology, but its homology will be spread out in at most n places. That's again a consequence of the fact that you can look into the proof, and you will see that in the proof we can use a resolution of length n. So this will be a complex of length at most n. So this is one way of looking at it. The complex that we write down here is coming from a soft resolution of S dot, and this soft resolution can be chosen. If you look at it carefully, it can be chosen to be of length at most the dimension of the manifold. So that will tell you that the dualizing complex F upper sheet K is actually having is living in n degrees, and those degrees will be from -n to 0. That you can see by applying this kind of duality theorem. That's one remark, and the other remark is, yeah, if it's a manifold, if it's orientable manifold, where so that this actually becomes, so I didn't say, one can define what is orientation. I mean, it should agree with the classical definition of orientation, and so one can define your manifold to be oriented in this case if this is the trivial sheaf, which will amount to saying that this global sections is not U but Hn x k tilde should be just be K. So once we define what is orientable manifold, then the co-unit map. So there will be a co-unit map. But if it's orientable, then it's just saying F lower Schlick orientation shifted by n to K. But then F lower Schlick is nothing but homology with compact support. So you can say something simpler. So that is just saying you are just looking at I hope I'm not making a mistake here. Yeah, that's what you are doing. And of course, it's orientable, so you can put K here. This is K. And now by duality, this is isomorphic to Hn x Ox. I mean, I meant Kx. I switched to the algebraic geometry notation. So this map is looking like this. Sorry. This has n homology and no other homologies, and so it will come down to this. But orientation n, you put it here, you will get and put Kx here. Then this will give you RF lower Schlick K. No, this should be K. Something has gone wrong. Okay, sorry. This is not that. So this will turn out to be C X, and this is isomorphic to H0. Okay. There's a natural map here. Anyway, so the co-unit map looks like this. But really, I'm interested in what this map is. And you can see what this map, you can guess what a candidate for this map should be. because especially if let's say k is your real numbers, then you're just looking at HNCX R tilde to R. And so for that, a natural candidate would be the integration. All right, so since time is over, I will, yeah, this place to stop.